Okay, so for this first problem, all we're going to do is sketch a free body diagram for the box. So it says a box is being pushed steadily up a ramp, which is inclined at 40 degrees above the horizontal. Okay, so we're just going to draw a free body diagram here. So we know that we're being inclined on 40 degrees. Okay, so let's do that. Of 40 degrees. Okay, and we have our, okay, so we're gonna have a box. A box is pushed steadily up a ramp. Okay, so we have our box. Okay, so let's draw our forces acting on the box. Okay, so first of all, we know that the force due to gravity is acting on the box, right? And always, that force due to gravity is acting straight down. And I'm just going to skip out on the normal force right now. But we do have the idea that the box is being steadily pushed up the ramp. Okay. Kind of like this. And that's our applied force. And we would also say that there is an opposing force, which is the friction force. And being that it's moving, it's going like that. Now let me tell you this, something that I didn't really discuss just yet is the idea of what does normal mean in mathematics? It means perpendicular. That's what normal actually means in the language of mathematics. So when we're talking about the normal force, we're going to say it's normal to the surface. If our surface is on an incline, hey, guess what? What's normal to it is perpendicular. So the normal force is going to be acting up on an angle like this. And this is our normal force. Keeping in mind, hey, you know what? It's going to actually make a 90-degree angle right in here, and that is perpendicular. Okay, so we have all of our forces on our free body diagram here. And the next thing to do would be to calculate out a given thing for this problem over here. Now, we're not going to do that in this, but hey, you know what? So all of these, look at this. This is going up and to the right. This is going up and to the left, down and to the left, and straight down. So if I'm to define all the forces going upwards are positive, and all the forces that are going to the right are positive, hey, you know what? What we're going to do is we're going to have a bunch of component vectors for each one of these vectors that is going up on a certain angle. Look at all of these component vectors that we'll have to calculate. What do you think about that? We got a lot of trigonometry ahead of us, I'll tell you that. Well, is this the most efficient way to go about doing this problem? I mean, there are so many different vectors that are, we would have to do a lot of trigonometry here and break down the component vectors. This kind of sounds like that would be a pain in the neck. So what's the reason why we had to do all of that? Well, we were defining that these are our positive directions over here. Up is positive and to the right is positive. Notice the idea that I said that we defined this. We defined that the upwards direction is positive and that to the right is positive. What could I do here to help us out quite a bit? Maybe instead of saying that these are our positive directions, what if we were to rotate these a little bit? What if I was to say this? Maybe this is my positive direction, and this is the positive direction. Hey, you know what? All we did was a simple rotation over here, and guess what? Now, this force is in line with this one over here. This force is in line with this one over here, and this force is in line with this one over here. The only force that's actually not in alignment with the way that we're defining our positive forces is this one over here. And for that one, what we'll have to do is, what I like to do is I just tilt my head a little bit and I look at all these forces as if this is pointing to the right, this is pointing upwards, this is pointing to the left, and which direction is this one pointing? Considering that when you are looking at this, you're just tilting your head a little bit. Well, you could actually say that this is pointing down and to the left. And once again, that would be the idea that's pointing down and to the left. And these are component vectors of our force due to gravity. So we have force due to gravity acting in the y direction and the force due to gravity acting in the x direction. And these are our two components. Okay, well, Okay, so, what's nice is that we did create another right triangle over here. How about that? But what else could you tell me about this triangle? I know that I'll have to use the trigonometry in order to find out these component vectors over here, but I don't have an angle in here. That's kind of annoying. I don't know what to do right now. Well, let's look at our bigger triangle. So let's try to get some context out of it. Okay, so what I'm going to do is this. I'm actually just going to drop a line coming down like this, and I'm going to drop another one coming down like this. Okay, and if I say that over here is angle, let's call it alpha, and we have these two lines right now, wouldn't you say that those are parallel lines? And if these are parallel lines, and we have a transversal coming through here like this, well then wouldn't you say that this here and this here are equal angles? Wouldn't you see that these two angles here are alternate interior angles where this is equal to alpha? Yeah, right? That's what we said in our do now. And if this is alpha and we have here a right angle, let me ask you something. What's the value of this angle here? We have alpha, we have a right angle. We have alpha, we have a right angle. What's the value of this angle? 40 degrees. So this here is 40 degrees. I'm just going to take this away. So once again, this in here is 40 degrees. That is, this all in here is the value of 40 degrees. I'm just going to erase a lot of this. And once again, what we basically said here was the idea that this is equal to 40 degrees, right in there. And this is our free body diagram.